Well, hello again, stellar material. Remember, I hopefully convinced you some time ago that you are star stuff because the elements that you are made of, the elements necessary for life, were actually made in stars. And we talked about this cycle that kind of looked like this. You have the birth of stars, so star birth, star leaves, that is, shines for depending on its mass, like the sun does. A star of a few solar masses, it does that for about 10 giga years, after which it dies and explodes and returns back into the medium in between stars, that is the interstellar medium, returns those newly created elements. Okay, so we're going to start with this lecture talking about the star births, and in particular we'll talk right now about those stellar nurseries, the regions where the stars form, and they can be extraordinarily beautiful. In fact, some of the most spectacular images that come from the Hubble Space Telescope are of starbirth regions. So what do we see in this beautiful image? We see one star and many of the other things here. The star is called Alnitak. It's the easternmost star in the Orion's belt. Okay, so one of those three stars, and I think it's kind of like this, the Orion Nebula in the sky. And this is the belt. And this is this one, the Alnitak, okay, one of those. So in between stars, there's a lot of what we call interstellar medium, ISM, the astronomers call them. And what is that? That's a lot of dilute gas that is in between the stars. And it is extremely uneven in terms of its properties, in terms of its density, in terms of its temperature, in terms of its composition. It is extremely uneven. But however, there are regions of very thin, hot gas and regions of much denser clouds of colder gas, and those are important for us because this is where the stars form. And as you will see, they look like dark regions, especially in the visible wavelength. Like this Horsehead Nebula, this is actually kind of famous. It does look like a horse, so therefore its name. There is no horse in there. Here's another one. This is the Emission Nebula called IC434. Here's another Emission Nebula, and we're going to see in a second what that means, and it has a different name. Okay, so this redder part, this is the nebula. There is a dark nebulosity, another region where we believe there are clouds of colder gas, and then there is a so-called reflection nebula, another name. NGC stands for New Galaxy Catalog. So initially that blob was believed to be a galaxy, but it turned out after more investigation that it is actually just a reflection nebula, which, as we will see in a second, is a region where stars are born. All right, so here are some examples of what happens when stars are born. And we're going to talk actually here a little bit about the one of the closest to us star-forming clouds or star-forming regions. And that exists right here, just under the Orion belt. So this is Orion Constellation. Somehow it looks like a warrior to some people, and therefore the name. There are some shoulders here and some arms with some, I don't know, some weapon of some sort. But anyway, this is the Orion belt, those three stars. You can identify that on the night sky if you look up. And so this is basically a star chart. This is what you see with the naked eye, or maybe with a good binocular telescope, the wide field of view. You see those white bright dots in the sky. Okay, so this is invisible, obviously, visible wavelengths. But let's look at how that particular region of the Orion Nebula looks like in infrared light. So it looks red. That's because we can assign that red color, right? Remember, we cannot really see that color per se, but right. So for our eyes are not sensitive to the infrared, right? We're only sensitive to the visible part. But anyway, in infrared light, you see this star, Betelgeuse. It's much fainter. That means most of its light, this star's light, is actually emitted in the visible. It's very little emitted in the infrared. But here is something else that shows up in infrared that was not visible in the visible light. Okay, so Orion Nebula, not really, intense in visible wavelengths. But look at that, right? It's really some of the most prominent things that we see in that field in infrared. So that is nebula. It's a bunch of gas where we later discovered there are actually stars forming right now. And right now is obviously in astronomical terms. So say for the past hundreds of millions of years, there have been stars forming in that region. Let's look at the other image that doesn't have much to do with the Orion part of the sky, but it does present yet another beautiful star-forming molecular clouds that are basically colder than stars themselves and emit in infrared. This is another image in infrared. I think it is obtained with the Spitzer Space Telescope. And it's actually a star-forming cloud in a constellation. So star-forming cloud in constellation Cepheus. You can look it up if you want. Okay? So we have infrared image here, and here's the same field in visible. Do you see any difference? You see the pink color in the infrared image represents the infrared light that's heated up from the stars behind, right? There is dust grains in the clouds, cold, dense gas that envelop the stars, okay? In the visible, right, in the visible light image, those things, that infrared emission is dark. Look at that. You can go back with the movie and just look at them before I scribble on them. Okay, so those grains of dust, they absorb actually the visible light. So it's the same region, right? And you see how it looks very different in infrared. In infrared, they glow with infrared light, but in visible, it's dark. It looks like there's nothing there. But obviously, there is a lot if you look in other wavelengths. All right, so these are both Orion Nebula and this nebula in this beautiful image. They're both examples of emission nebulae. So what happens here, you have a bunch of hydrogen atoms that are ionized by hot photons from newly formed stars, and those electrons actually come back and recombine with some other protons and form new hydrogen atoms, but they're going to form with the electron in an excited state. And because nobody and nothing actually in this universe tends to stay for long in an excited state, it's going to de-excite, it's going to emit one specific type of radiation, one specific wavelength, which is actually what we see in the emission nebulae. Okay, so those were examples of emission nebulae, but here are some other types of nebulae. We have the dark nebulae. Here is the example, and the reflection nebula. Nebulae, that's the plural from nebula. All that's Latin, so there are no nebulas, although some people use that. All right, so here's an example of a region in the sky that appears dark, invisible wavelengths, okay? But then we looked in the infrared and actually saw a bunch of heated dust, okay? So those are often called by astronomers as holes in the heavens. So they're opaque regions that block out light from the stars beyond them. Now, sometimes that veil of dust that envelops the stars do other things, like they reflect the light coming from the stars that they surround, and in this case they appear as reflection nebulae. Like in this case, they're often blue in color. All right, so those regions in which stars are formed, what else can I say about them? Like, what are basically their properties? What's their mass, composition, temperature, density, and so on? So let's go through a few of them. How much mass is there? Like, some would say before they took this class, like, how heavy are those? Well, it's kind of hard to talk about the force of gravity, right? Because when you talk about how heavy something is, you talk about the force of gravity. But we can talk about just how much mass is there. So you have a few hundreds to a few thousands times the solar mass, okay? So basically a few hundreds or a few thousands of stars like our own put together in that clouds. That's how much matter is in there. What kind of matter is in there? That is, what's their composition? So it says there, it's the usual mix, right? Remember, universe, that is 74% hydrogen, 24% helium, and the rest, everything else. The rest of less than 2%. And that is definitely true for these nebulae that give birth to stars. Okay, how do we know what's inside, okay, in those gas, that is, atoms, molecules, what kind of molecules? There are microscopic dust grains and possibly larger objects, but it depends on how cold actually that region is. So basically how able are the molecules or atoms to stick together to form larger objects. How do we find out what kind of object? It says here carbon and iron and silicon. Well, you measure the intensity as a function of wavelength, right? And in this case is some background stars. You measure a star. Remember, it's going to look like that, right? That's the spectrum of a star. But then there are, some things. Most of the absorption lines come from the star itself. But in this case, and actually in this case, it's kind of this region, right? So this spectrum, now it's blown up, right? Here, and we see a lot more features. So this is a really high resolution spectrum. So kind of just a tiny part, right? So it would go from 1 to 6 nanometers to 1 to 6.2 nanometers, right? And we see all kinds of features, and we can measure their wavelengths, and we can measure like how much flux is missing, how much intensity, and we can calculate the amount of basically everything else. What other things we detect there, like carbon, iron, or silicon. All right. Now, how dense are these molecular clouds? Okay, so you might be in for a surprise, but guess what? 150 kilometers cubed, basically a volume of this many kilometers cubed, 150 of the material in that cloud contain one lung full of gas, your lung full of gas. So imagine how spread out that is, right? So you can look at this number, right? Obviously this is to the power of 3 here, atoms, 300 atoms per centimeter cube, okay? So that is in average, but then sometimes there are these dense clumps of, look at that, orders of magnitude higher than the average, right? So we have orders of magnitude higher than the average, okay? And these dense clumps are where it's very likely that the stars form. There are some other parameters that are necessary for that star formation to happen. Okay, the temperature, especially for those regions, for those molecular clouds, needs to be very, very cold, right? So in terms of Celsius, if you want, that's 273 Kelvin. That corresponds to 0 Celsius. This is kind of like minus, 200, at least minus negative 200 degrees. Okay, just to give you a sense of how cold it is in there. So basically, right, remember our definition of temperature, not just the definition. What determines the temperature is the average kinetic energy of all those particles that make up the molecular clouds. So the gas, which is in a form of molecules, right? So we have, usually that is an H2, H2O, which is the water, NH3, ammonium, C2H5OH, and I forgot the chemical name for that molecule. All kinds of molecules that have some carbon, a lot of hydrogen, some oxygen as well. So anyway, the molecule of hydrogen is by far the most common. However, it's very hard to detect because it cannot emit radiation. It is the neighboring monoxide of carbon that emits radio waves, and it goes like this. We're looking for those star-forming clouds, and we're often using the radio emission associated with those CO molecules to as a proxy for, hey, this is where we actually find any molecular gas, especially the hydrogen molecular gas. So that's how we find the regions in which stars form. So this is again Orion Nebula. This is the Orion belt. Let's see if we can do better like this, maybe. Okay, and here is how the emission in 2.6 millimeters, so that's a radio emission, radio detection. This is where the radio emission happens, and you can probably distinguish how this strong, intense radio emission is associated with basically Orion Nebula, which is a stellar nursery. This is how we find them. Okay, now how large are those dust particles that we're talking about? Are they, you would think, like the dust bunnies in your bed? I don't insinuate that you have those kind of things under your bed. Just in general, it's very possible that they gather down there. It turns out that the particles that make up those clouds, the molecular clouds, are actually tinier than that. They're the size of the human cell. Okay, so that's barely distinguishable or resolved by the human eye, and it contains a lot of carbon, silicates, iron, and ices. Pretty much the things we've seen in the spectrum in the previous discussion. All right, another interesting kind of cool fact about the interstellar dust, or the dust grains. So these are again high resolution image of dust grains, and you already probably noticed their color. It turns out that dust, or the dust particles, they appear red because they are very efficient in blocking the blue light, the shorter wavelength light, and a lot more effective in re-emitting or scattering the red light. Here's an example. Again, we have a dark nebula. This is how it looks like in visible wavelengths, and here is how it looks like in infrared. Do you see any difference? Well, first of all, here is nothing, right? So these are stars that can be seen. Because dust is not as prominent, because of basically less dust in that region. Here, more dust. So thicker veil of dust. But it is this exact region, right, that in infrared reveals. So infrared detection or observations reveals stars. And then we measure their properties and we realize those are newly formed stars. Okay? And they're also red. Redder color. And that is due to the fact that the particles of dust are more efficiently scattering the red light than the blue light. The blue light is actually blocked, so it doesn't go through. Yeah, so this is another example of the fact that dust reddens, and also that this reddening process depends on the distance. So here are, for example, two nebulae. This is a closer one, so not as red enough because there is dust that scatters light that's coming from the stars, and even if that light is blue, the light coming from stars is going to be scattered at longer wavelengths, so it's going to look redder. But this more distant nebula is even redder. So sometimes, we look at things through the telescope and we see them red, and most of the time actually it's going to be very hard to tell whether that thing is red because it's far away or because there is more dust that makes it red. So, one of the conundrums for astronomers when they want to interpret their observations. Now the question is, you might have wondered, where exactly are these stars forming within the galaxy, right? So where are those molecular star-forming clouds? So now remember our Milky Way, it does look like the way of the milk, right? Because we see our galaxy edge on, because we are in it, in that pancake. We are that grain of flour inside the pancake, and we're looking through the pancake, okay? And so, yes, we see the milk spilled out there, but we also see some dark lanes, especially if we have a really good binocular or is a really nice dark night somewhere far away from the stadium lights. And yeah, those lanes of interstellar dust are those star-forming clouds, the molecular star-forming clouds, and they are concentrated close to the mid-plane of the Milky Way galaxy. The mid-plane, just like here. Okay? All right, this is the ionized hydrogen regions we talked about. So the Emission Nebula, or Nebula for now. All right. Okay, and here's, for example, a face-on view of a galaxy like Milky Way, very much like our own galaxy. And you see there are these spiral arms, and it's in the spiral arms that we identify those emission nebulae. That is where the stars. Now why is it that stars form in some regions, in some regions of the interstellar medium, and not in others? Well, it turns out in any region of gas, there are always at least two forces at work. The most important one, the one that actually, if it wins, if it's strong enough, it's going to produce that new star. It's the gravity that pushes inward. This is the force that is going to make the gas collapse. Nevertheless, there are other things that support the gas and prevent the collapse. Okay, so there are many things, and some of them is, well, for example, just how hot maybe that cloud of gas is, because the particles move around, you know, like this. They have enough kinetic energy to push in all directions. That's called thermal pressure. Sometimes there is bulk motions, not just individual atomic motion, just atoms kind of move together, and that's called turbulence. Or sometimes there are magnetic fields, or sometimes the cloud rotates, that adds more motion that is going to prevent the push inward of the gravity. And so throughout most of the interstellar medium, the gravity cannot win in most of it, right? There are just the massive, dense, and cold molecular clouds that the gravity can win. Otherwise, it would be stars forming all over the universe, and it surely doesn't happen. Okay, so you might or might not know much about how the solar system formed, but it looked something like this. We have a cloud of gas. You can imagine a three-dimensional thing, kind of like a sphere if you want. If actually there is plenty of matter in it, it's going to have a shape close to a sphere. It depends also on what forces act on it from nearby. If there are strong winds from supernova or some other things, it's going to deform it, make some holes in it or anything. But anyway, that original cloud, it's large and diffuse. Large and diffuse. And its rotation is actually imperceptibly slow. So yeah, there could be some rotation, but it's not much to talk home about. Okay, but anyway, at some point the cloud begins to collapse because the gravity starts winning, and so begin collapse. And what's going to happen? The cloud loses potential energy. Is lost, but is actually converted to kinetic energy, right? Conservation of energy. And so it's because of that, right? So potential energy is lost because the size becomes smaller thanks to the collapse, okay? And the potential energy is directly proportional to just how big things are. It's becoming smaller, potential energy is converted into kinetic energy. And so the cloud is going to heat up because the particles are moving faster and faster. So more kinetic energy, particles move faster and faster, okay? And also the spin is going to be faster and faster thanks to the conservation of angular momentum. So pretty much what happens to the skater when they pull the arms in, right? And that little tutu becomes flat like a disc. That's exactly what's going to happen here. So the gas, the cloud of gas flattens. Okay, the gas settles into a spinning disk because the spin hampers the collapse perpendicular to the spin axis, right? So we end up with a disk of matter, that is gas, of course, around a very hot core, very hot, very high pressure as well. This is where the star is born. The disk around it is where planets are going to form. The disk, this is where planets will form later on. So that's the scenario that, it kind of works with pretty much all the observations we have conducted about stars and disks of matter around stars, like obviously the way the planets in our own solar system move. And also, of course, we have observations. We also have some computer simulations, okay? And while the exact details of the gravitational collapse that gives birth to stars is not very well understood, we do have actually a pretty good idea, right? So basically, here is an example of a simulation that begins with we have a turbulent cloud of gas that is going to actually fragment. There are random motions of the cloud that cause it to become lumpy, and some regions are going to end up denser than others, right? So this and this, for example, are going to be denser regions, and that means gravity is stronger and it has chances to win. Basically, it's going to collapse. It's going to fragment. All that big cloud is going to fragment into many smaller lumps of matter. And you see that in those bright yellow regions. And stronger gravity wins. A star is born. Actually, many stars are born. A cluster of stars is born. So that's about it in terms of where we find and what those stellar nurseries.